Certain compounds, mostly those with chiral carbons, rotate the plane of polarized light. The angle of rotation depends linearly upon the type of sample, the concentration of an optically active component, the length of a sample tube, the wavelength of the light source, and the temperature of a sample. In order to define the relationship between a concentration and an observed rotation and specific rotation, we will make a best fit line on Excel. We're going to measure the observed rotation with a polarimeter at different concentrations of an unknown sample. In this lab, you are going to need these items. First, you are going to make a 50 milliliter sugar solution with a concentration of 0.1 gram per milliliter. To make this solution, you will need 5 grams of sugar and 50 milliliters of distilled water from this calculation. So first, measure 5 grams of unknown sugar. Using a funnel, transfer the sugar into a 50 milliliter volumetric flask. Rinse the funnel with distilled water to wash any clinging sugar. Fill the flask about 3/4 full with distilled water. Cap the flask, invert, and shake well until the sugar is dissolved. After the sugar is completely dissolved, fill the flask with distilled water until the bottom of the meniscus sits on the tick mark. Now we are going to introduce how we make solutions with other concentrations using the original 0.1 grams per milliliter solution and distilled water. In this video, we're going to give you examples of 0.04 and 0.08 grams per milliliter solutions. In order to calculate the volume of the original solution to measure, use this formula. For example, when you want to make 10 milliliters of 0.4 grams per milliliter solution, the initial concentration of the original solution is 0.1 gram per milliliter, the final concentration is 0.04 grams per milliliter, and the final volume is 10 milliliters. X in this case is what we want to know, which is the volume of the original solution you need to add. So now you can build this equation and solve for x. X is equal to 4. So now we know that we need to add 4 milliliters of the original solution and 6 milliliters of distilled water to make 10 milliliters of 0.04 grams per milliliter solution. Using a graduated cylinder, measure 4 milliliters of 0.1 gram per milliliter solution and 6 milliliters of distilled water to make 10 milliliters of 0.04 grams per milliliter solution. Now we are going to show how to use a polarimeter. First, turn on the switch on the back of the polarimeter. This is a polarimeter cell. You need to handle this carefully. You can touch wherever is convenient except the lenses on the sides because this is where the polarized light passes through the solution. Before testing the sugar sample, you need to calibrate the polarimeter with distilled water. Fill the cell with distilled water to at least the bottom of the cup. Place the cell in the polarimeter carefully, close, and zero the polarimeter. The number on the polarimeter should be 0. Dump the distilled water carefully and add the test solution into the cell. Place the cell, and it automatically reads and shows the number on the polarimeter. After recording the number on the polarimeter, dump the solution and wash the cell with distilled water. Also, before making any other concentration solutions, wash the cylinder with distilled water as well. Now we are going to show the example of a 0.08 grams per milliliter solution. Do the same calculation to find how much of the original 0.1 gram per milliliter solution you need to add. From the calculation, you add 8 milliliters of 0.1 gram per milliliter solution and 2 milliliters of distilled water to make 10 milliliters of 0.08 grams per milliliter solution. You don't need to calibrate the second time. Add the solution into the cell, place it, and record the number on the polarimeter. In order to understand this experiment, it is important to understand these equations. This alpha is an observed rotation of polarized light we get from the experiment. The bracketed alpha is a specific rotation, which is experimentally determined value. Every compound has a specific determined amount of rotation and of polarized light. C is a concentration measured in grams per 100 milliliters or grams per decimeter. L is the path length measured in decimeters, which in most cases is 1 decimeter. If we manipulate this equation by eliminating 100, this equation can be more useful for this experiment. Now concentration can be measured in grams per milliliter, and the length of the polarimeter tube would still be measured in decimeters. Here you have a column for the concentration and a column for the observed rotation. We need to make a graph and add a trend line. Once you have your trend line, display your equation on the figure. This will help define specific rotation of our data. Ideally, you want to have a linear equation of y equals mx plus b. This linear equation can be compared to the equation of alpha equals bracketed alpha times c and L, where bracketed alpha can be compared to the slope of the linear line. As you can see, our slope is 50.371. Now we can compare it to the chart on the instruction and decide which sugar has the closest specific rotation. We just saw that the slope of the equation is 50.371, which is the closest to the glucose specific rotation value, 52.74. So we know that the unknown sugar was glucose.